Okay, so we're looking at statistics. We're going to look now at, I suppose, the two statistics, if you like, that we will primarily be working with, really, particularly when it comes to what we call inferential statistics, okay, where we're trying to basically infer, I suppose, which is kind of in the name, we're trying to infer some characteristics or some values essentially for particular types of statistics. Okay, and the two we're looking at are proportion, okay, the population proportion, and then the population mean. Those are really the two statistics or the two values that we're going to be kind of working with, kind of calculating or approximating or kind of testing different claims around. So everything kind of revolves around either proportion or mean. And we'll look at examples of both and how even for, on the simplest level, maybe how we would tell the difference between the two. But we know with statistics, we know that the population refers to the entire possible group that's being examined. So if I'm asking the whole country, that's a census, for example. But if I was asking or doing research on Leaving Cert students, then the population would be every single Leaving Cert student in the country. Obviously, that's not really reasonable or feasible to study every single Leaving Cert student in the country. So instead, we would usually take a sample, which is just a smaller group that I take from the population, and it's used as a sort of representative. Okay, I might try and kind of infer something about the population based on the sample that I have. Okay, so what we're looking at, I suppose, in this first section is looking at population proportion here, okay, which is given by the letter P. And obviously a proportion, we're kind of thinking maybe percentage, or we're thinking kind of a fraction or a decimal. Okay, those are the three things to me that I would consider proportions. So fractions, percentages, decimals, maybe primarily even a fraction or a percentage to me would be kind of indicative of a proportion. Um, I suppose in fairness, decimals, yeah, it's all kind of the same, but just different kind of, different ways of saying it. Um, so the population proportion is the proportion of the population which have a particular characteristic. So the example here I have even is that it might be we might want to know the proportion of Leaving Cert students who are going to study medicine. So we would find the number who are going to study medicine and write it as a fraction of the total number of students. Or we might look at a particular political party and find the people who voted for party X and put that as a fraction of everyone who voted. So we're essentially trying to work out a fraction or a proportion of people that voted a certain way, or that are intending to do it a certain course, or that kind of satisfy a condition that we have. Now, generally, we will not know this value, okay, based on what we said already. Population proportion, you're not going to ask every single person in the population, it's just not realistic. So we're more likely to ask a sample. So based off that, then, rather than having population proportion P, we are much more likely to have sample proportion, which we kind of illustrate here or kind of denote by P hat. Okay, so the P here, which has the little kind of hat, or um, it's that is it has a name, I forget it. It has a name in some of those languages, the little kind of hat shape arrow thing on top of them. Anyway, sample proportion P hat is what we're looking for. Okay, and it's the proportion of the sample to which this applies. Okay, essentially this is an estimator. Okay, I know I'm just kind of highlighting words here, but it's kind of good for us to know the theory here. So the idea is basically we take this sample, we find what fraction of the sample it applies to, and then we're using that as kind of a generalization then for the population. We're saying, well, in the sample it was maybe 30%, so we could maybe say that is around 30% in the population as well. Okay, and a lot of that then is going to come down to maybe how accurate is your sample, how could I make it more accurate, how accurate can I be without just asking everybody in the population, and all of these are questions that come into kind of our calculations here. An important note that we have here is just to say that both of those generally will be expressed in decimal form. Okay, and I know I did say like fraction, percentage to me are kind of indicative of proportion, but when we're actually writing these down, we're going to use decimals. Okay, we're going to use decimals. It's just kind of cleaner, and a lot of the answers we're getting won't work out as kind of nice fractions. So it's kind of just easier just to go for decimals straight away, and then you kind of, you're going to probably end up in decimals regardless. So it's nearly better to just start there. So Naturally enough, if I take a sample, okay, based on what we've said, and I'm sure you should be thinking that for yourself, if I ask every Leaving Cert student in the country who's going to study medicine, that proportion is likely to be quite different to if I just asked one particular class of Leaving Cert students in a particular school. Because you could have a school where everybody wants to study medicine, you could have a school where nobody wants to study medicine, you could pick a particular class where there's just not that many people who want to, or there's more than normal amounts of people who want to. So a sample just is never going to be completely indicative of the actual population. So there's always a possibility of error there. So rather than us saying that my sample is definitely the exact population proportion there, we allow for some sort of error. Okay, and this is our margin of error. So we say, yeah, okay, I took a sample and in the sample it was 27%. So I'm not saying that the population one is exactly 27%, but I might say it's in or around, and we could say 20, we might say 30 and 24. For example. So looking at kind of what I'm saying there, maybe if we start at 27 here in the middle, I might be saying, yeah, okay, it's probably not 27 though, but it could be between 24 and 30. So I'm allowing myself maybe 3% either side of the 27 there. I'm saying, yeah, maybe not exactly what I got for my sample, my p hat, but somewhere either side of that it probably does fall. And that's my margin of error. I'm basically saying there that I think I'm probably right, or there's about a 3% error that I'm accounting for here in my calculation there of my p hat, of my sample proportion. Okay. And we've two different ways of working out margin of error when it comes to population proportion. The first one is quite, I suppose, what's the word? It's a bit kind of rough and ready, I suppose, to some extent. It's the margin of error approximation, okay? And it's this one in the box here, 1 over square root of n, where n is the sample size. Now this, again, it's an approximation, okay? It's an approximation of the error. It's maybe how wrong approximately we might be, or how much error we need to account for. It works at the 95% confidence level. So what that means is we are 95% confident that the true value will be within this margin of error of the population of the sample proportion there. So say for example what I had on top there, we might be 95% sure that the actual population proportion is within that range of 24 to 30 if 3% was my margin of error there. So it's important to know as well, so the notes we have here only works at 95% confidence, so you'd look for that in the question, should only be used when requested, okay? And that's primarily, that's only just at higher level, okay? At higher level we only use this approximation when it's requested, because at ordinary level this is kind of the one we would go for. Higher level we have an extra one that we can go for that is more accurate. Again, decimal form, which is what we've been saying here. And the last little note is something that hopefully we could recognize even just from the function itself, but as n gets bigger, so as that gets bigger, the fraction itself is going to get smaller. So if my sample size gets bigger, then the denominator will also get bigger. But as we know, even from our work on limits, as the denominator of a fraction gets bigger, the fraction itself is getting smaller. So the way to make your sample or your margin of error smaller is to increase your sample size, which makes sense, because ideally then if we make our sample size as big as possible or take the entire population, our margin of error should be basically nothing. So looking at calculating this margin of error and this approximation here, so we know calculate the margin of error for a sample of size 150. Well, we know that the little formula here is 1 over root n. If it's sample size 150, 1 over 150, and that will give me 0.081649, which if I was then to write it as a percentage, 8.16%. Okay, so for a sample size of 150, there's about an 8% margin of error there within that sample size. So that's quite a little margin of error there. We wouldn't be entirely accurate. We're allowing for basically 8% either side, so a total of about 16% of error there. Then calculate the sample, which will give an error of approximately 2%. So we're basically saying here I want to calculate n so that my error is 0.2. So I might square both sides to get rid of my square root. That's going to give me 0.2 squared, 0.04. And multiplying, dividing here, which means n is 1 over 0.04, which is 25. So a sample size of 25 here would give me a margin of error of approximately 2%. Okay, so margin of error approximately 2% there or sorry, excuse me, I've typed that incorrectly. Sorry. I was thinking that error was very, very small, 0.02. I do apologize. That makes much more sense though. 1 over 2,500, yes, of course. And of course, then n is 2,500. Much more accurate. I was thinking there to an error. How could I have a 2% chance of error with only 25 people? Very, very small. So we can see even there, just from that example here, increasing my sample size from 150 to 2,500 has really reduced my error there from 8 to 2%. So looking, I suppose, or going a little bit further then, I said there was a much more accurate way of doing this, and that's going to be using what we call the standard error here. Okay, so the idea in the standard error is that I, as we know, can take a sample and work out the proportion in the sample that this applies to, which is my p hat. And if we are to take many, many samples of the same size and do that for all of those samples and work out the proportion that it applies to in all of those samples, those proportions themselves would be normally distributed. Okay, and it's called the sampling distribution of the proportions. Okay, so we're basically saying I take loads and loads of these different proportions from all my samples and then nearly represent those as a distribution. So you're thinking of like a histogram here, and I'm putting in maybe how many times all of these different proportions appear, and that should take a normal distribution. Okay, the standard error of this normal distribution, okay, and that's I suppose standard deviation here, represented by sigma p hat, is a much more accurate measure of the margin of error, okay, for my sample proportion or for my population proportion here. Okay, so this standard error would be given to you. Okay, it's in your formula and tables book, so you just need to remember where it factors in here. So we had that margin of error approximation previously. Now we have this standard error, this kind of standard deviation nearly for the population proportions, and it's basically us saying, I suppose, how far from the actual population proportion is this sample proportion likely to be on average. You know, on average, how far are these kind of sample proportions from the actual population proportion? And as we can see here, the standard error uses p in its calculation. Okay, we can see that on the left here. So p and 1 minus p. Now, as we know, p is the population proportion. We will very rarely, if ever, know the value of p, the population proportion. So because of that, we will more often use p hat in our calculation. Okay, so we've said p hat is an approximation of p, and because of that we're going to use in these calculations. Okay, so just even to note maybe, and I suppose the only reason that I'm kind of bringing it up is, well, I suppose it is the formula, so that's the first reason, but also that's the way the formula is given to you if you were looking at it in an exam. So I don't want you looking at it and kind of going, that's not the way that we learned it. You would just use p hat as normal, okay, unless p is known, and that can come up very rarely in particular questions, say like flipping a coin. When we're flipping a coin, p in that case for the proportion of heads should be a half. Okay, that's what the proportion should be. So that might be p in this example. So there we might use that value of p as opposed to the p hat that's identified in the question here based on my samples. But taking that standard error, okay, that standard error can be used then to create a margin of error. Okay, so the difference, I suppose, between standard error itself as kind of this standard deviation of the sample distribution of the population proportions, which is a mouthful, and also using that then to work out your margin of error. Okay, so more closely related to that 1 over root n. So the margin of error is 1.96 times this standard error, sigma p hat. Okay, the reason for the 1.96, to dwell on that a tiny little bit, is kind of identified here in this z-score diagram. So if we look at the diagram here, 1.96 standard deviations, okay, considering both positive and negative versions here. If I look at the proportion or the percentage of information that's included between those two bounds of plus and minus 1.96, that would include 95% of my information here, okay, which is a great amount of information to be included. And what that means is we can be 95% confident that the actual value would fall within that range there. Okay, it basically means that out of however many samples or however many things that I do, I would expect 95% of the time that I would get a result within there. Okay, so using my 1.96 here basically is me accounting for that, okay, and that idea of my 95% confidence. There's always a 5% chance that we're wrong. Okay, there's always a 5% chance that it doesn't fall within this range, or that it's outside kind of the range that we've identified here with our margin of error, but there's a 95% chance that it does fall within that range, which is about as confident as we're really willing to get, because more confidence kind of has an impact then on the margin of error as well. Okay, so thinking about kind of the margin of error here, if I increase my margin of error, that would mean increasing this value here. So say I went to 2.5, that would mean I'm multiplying here by 2.5, and therefore my margin of error would be larger. Okay, so to include more information within the range here, I would need to extend my margin of error. Okay, and that's something we're not necessarily willing to do. Okay, so we allow slightly less confidence to ensure a little more accuracy. As I've said already, since we don't know the value of p generally, we'll usually use p hat then in calculating this margin of error. Okay, so we're going to continue onwards. We're going to look at confidence intervals for the population proportion. So this is kind of what we've been building up to and what we've kind of essentially alluded to the whole way through here. A confidence interval basically is a range of values within which I think the true value of the parameter is going to be. And by parameter, I mean that population proportion P. We are going to look at 95% confidence. Okay, that's what we need to look at for our course. And that means that the probability that the true value is within our interval is 95%. And as we've said, there's that 5% chance that it's outside the range. Okay, as I kind of said in the previous part there as well, we can technically create intervals that are at different confidence levels, like 90 or 90, 97 or whatever, but that would require us to change that 1.96 that we saw in the margin of error formula. And generally, increasing confidence means increasing my confidence interval and a greater margin of error. Okay, so I'm basically, if I want to be more confident about my answer, I make my range of values bigger, which kind of makes sense. Okay, if I'm saying I'm 95% sure that it's between 10 and 20, then it's reasonable to say that I'm maybe 97% sure that it's between 8 and 23. Okay, I make the values bigger. Okay, I look at a wider range. That kind of makes kind of logical sense there. Looking at 90%, we would use a smaller z-score, so that margin of error would be smaller, but again, we would be less confident then about it falling within that value. But all you need to know really is that we're focusing on 95%. So to construct a confidence interval, we use the sample proportion and the margin of error that we've already defined. Okay, so basically, we are saying that the true value p for population proportion will lie between p hat plus the error and p hat minus the error. So basically p hat plus or minus my standard error here. Okay, and depending on what our error is, that kind of gives us nearly what we call like the radius of the confidence interval here. So kind of how accurate we're allowing this confidence interval to be. The notes as well, we use the standard error unless we're asked to use the 1 over root n. So unless we're asked to use the 1 over root n, we are going to be using the standard margin of error here, which is the 1.96 times square root of p and 1 minus p. This is my sigma p hat here. Okay. The other thing I would say to you as well to just be very, very careful of, because maybe I haven't just emphasized it here, the 1.96, okay, looking at our log tables, if you were to look at it in the Formian tables book, is not included. Okay, the sigma p hat is included, but the 1.96 is not. So just to remember, and I suppose that's why I've kind of emphasized nearly where it comes from there, just for you to remember that the 1.96, that's the part that gives us that 95% confidence. So without that, we're really reducing the confidence that we have. So we must have that 1.96. Let's look at an example and get into some exam questions then for constructing these confidence intervals. So a company is looking at the proportion of workers who went on sick leave. A random sample of 20 employees is taken, of which 9 have been on sick leave. Construct a confidence interval. Okay, let's start by finding p hat. P hat is the proportion of my sample. So it was 9 out of the 20 workers in my sample. So let's see what that works out. 0.45. So the sample proportion is 0.45. So basically 0.45 of people within the sample had been on sick leave. We're asked to construct the confidence interval using two different margins of error. We're going to start by making note as well of our formulas here. So starting off, p hat plus 1 over root n, p hat minus 1 over root n. Okay, maybe taking this time for us just to note as well, the 1 over root n only works at the 95% confidence level, so I don't include the 1.96 there because I don't need to. Okay, it's defined at 95% confidence. So let's just calculate these values here. 0.45 plus 1 over root 20, and that's going to give me 0.634. And then if we do minus 1 over root 20, that is going to be, oh, sorry, I've multiplied there. That is going to be 0.226. So we are basically saying that the true value for population proportion will lie between 0.67 and 0.226, okay, based on my margin of error approximation. If we try and do this now with our standard error approximation, we need to change our formula slightly. So p hat plus 1.96 times the square root of p, 1 minus p over n, and the same on the other side here. Okay, oh, not forget 1.96. Okay, remembering as well what we said here, p is generally unknown as it is here, so in our formula we're going to be using p hat in our standard error calculation. That's absolutely fine. So 0.45 plus 1.96 times root 0.45, 1 minus 0.45 all over n, which is my sample size, so that was 20. And let me see here, I might get rid of this line to give me a little bit more space. 0.45 minus 1.96 root 0.45, 1 minus 0.45. Bear with me, I know that is tiny, but we'll be doing the calculation now on the next line. So let's work it out. And you could, of course, work that out ahead of time. Just not forgetting my 1.96. So 0.45, 1 minus 0.45 all over 20 as my sample size here. And we get 0.668. And changing this now to a minus as well, 0.232. Okay, so we are basically saying, based on the margin of error using the standard error there, that it's between 0.668 and 0.232. So we can see slightly more accurate there using the standard error formula. Okay, making a conclusion. Okay, so we might look at the standard error for that one. It says which is more accurate, so that's the standard error. If I look at that, I am saying that p is within 0.668 and 0.232. If we look at what the claim or what they've said here, we're basically saying, or our conclusion here, is that we can be 95% confident that the proportion of workers who went on sick leave was between about 23.2% and 66.8%. Okay, still quite a wide range there within it, okay? And obviously that's going to be largely down to the very small sample size of only 20, okay, which gives an awful lot of error there to our kind of estimation, I suppose. Okay, so it allows for quite a bit of or quite a large margin of error there. Okay, just to even consider as well here, the margin of error. Okay, we have to think about how p hat plus the error was 0.668. P hat minus the error was 0.232. If I subtract those, that's going to give me twice the error, which kind of makes sense here. We're basically saying that from here to here, is a distance of the error, and then from here to here is also a distance of the error. So if we need to work out that error separately, sometimes what we can look at is the difference between the kind of top and bottom of our confidence interval there. Okay, and that can help us then in calculating that error itself. Okay, all of these things, I suppose, important for us when working with these confidence intervals, and just kind of all important to consider. So we'll look at an example or two here. I think we'll not get into too many with our confidence intervals. They come back up quite a bit in some of the later sections here on hypothesis testing, so that might be the one to go to next. But looking at kind of the first example here, a survey on remote learning was carried out of a random sample of 400 students. That's important. 135 of the students preferred remote learning. That's important. Work out the proportion of the sample that preferred remote learning. So of the sample, so p hat, because it's sample proportion, it was 135 people out of 400. It says to 4 decimal places, so let's do that. 0.3375. Next question asks me to use the margin of error approximation to create a 95% confidence interval. So I know my 95% confidence interval, p hat plus the error, p hat minus the error. They've told me here to use the standard, or the margin of error approximation, which is 1 over root n, so that's what we'll use. Okay, let's fill in any values we can. We know the proportion here is 0.3375. We know the sample size was 400. I'm expecting that that will cause a smaller margin of error than we saw, say, in the first example there. So let's try it out. We'll just fill this value in. 0.3375 plus 1 over root 20 gives me 0.5611. And on the other side then, subtracting the error there, I don't know why I keep hitting multiply, 0.1139. So we are basically saying, did I fill in 4? Oh, sorry, excuse me, I only filled in 20 there. Disaster. Okay, let's try that again. 0.2875 and 0.0.0169. Okay. Oh my god, I hit multiply again. This does not want to cooperate with me today. Okay, there we go. Much better. Okay. We are basically saying that we think that the true value for population proportion lies between about 0.2875 and 0.3875. Okay, so we're giving ourselves about an error there of about 0.0, or about 0. 0.0 kind of 1 in total there, and maybe 0.05 kind of either side. Okay, let's look at that now using the more accurate interval. So we should know that the more accurate interval is using the standard error. So that's p hat plus 1.96 times my sigma p hat. Okay, I'm just going to use that notation here because I'm conscious that that is how it's given in the formula and tables book. So let's get used to that. So let me remind myself, it was 0.3375. As I should have there. 0.3375 minus 1.96 times the square root. Okay, I'm using p hat here within this formula again. We know that it does say p in the formula and tables book. However, p is generally unknown. So because of that, we will use p hat here to approximate its value. 1 minus 0.0375 over 400. Okay, let's calculate those values here. That's going to give me an overall value then of 0.0375 plus 0.0463, and then the same on the other side, 0.3375 minus 0.0463. So my population proportion then is between 0.3838 and 0.2912. So we can see, even comparing the two there, we get that little bit of extra accuracy using the margin of error, using the standard error there. It is only slight, it's only slightly more accurate there, but it is more accurate nonetheless. Okay, we'll look quickly at the last two examples coming in here. Trans-Sky Airways surveyed 2,500 of its passengers about a new service. The variable p hat is the proportion of respondents who said they would use the new service. The radius of the 95% confidence interval of the survey was 0.01568. Find the value of p hat where p hat is between 0.5 and 1. Okay. The basic summary of this one here, okay, is this use of the word radius of the confidence interval. And what they mean by that is margin of error. Okay, what they mean by that is the value or the kind of error we're allowing either side of the true parameter here is 0.01568. So that is to say then we'll try 1.96 times the square root of p hat 1 minus p hat over n should be equal to 0.01568. So filling in these values now. Okay, we know what n is because we know the sample size, so we can fill that in. I'm dividing by the 1.96 here to get 0.008. Okay, at this point I might want to square both sides to get rid of my square root here. I'm also going to multiply out that bracket on the top of my fraction. 0.008 squared, well, that's going to get immediately quite small, so let's move to a fraction there to account for that. We basically have the p hat minus p hat squared is, let me multiply this by 2,500 to get 0.16. Okay. Then bringing everything to one side here, p hat squared minus p hat plus 0.16 equals 0. Okay, that now is a quadratic. Okay, we can solve the quadratic in any number of ways that we want to. Okay, we could go straight to our minus b formula. We could solve it by factorizing. I could multiply it out here to get 25 p hat minus 25 p hat squared minus 25 p hat plus 4 equals 0. I would need two numbers that multiply to give me 100, but add to give me 25, so 20 and 5. Okay, and basically what we're going to end up with here is that p hat is equal to 0.8 or p hat is equal to 0.2. Because we've been told in the question that the p hat value is between a half and 1, we have to go with the 0.8 there. Okay, but all of this reliant upon you recognizing that reference to radius of the confidence interval and making that connection between that idea and the margin of error. Okay, and that just relies on you having that little understanding that margin of error is maybe what sort of kind of how far from the parameter we're kind of willing to accept to some extent. Okay, that's kind of the best way of describing it, kind of how far from. And within that confidence interval, yeah, I suppose the radius, it's kind of the distance from the center or from P that we're allowing. We'll look at one more. Motoring magazine collected data on cars on a particular stretch of road. Certain details on 800 cars were recorded. The ages, 174 of them were new, less than 1 year old. Find the 95% confidence interval for the proportion of new cars on this road. So the first thing would be to find P hat, which is 174 out of 800. 0.2175. Yeah. Okay, I'm not directed to use any particular margin of error here. However, when it's not mentioned, I will lean towards the standard error as it is more accurate. Okay, we obviously know the standard error here usually uses P, but that's very, very rarely, if ever, known. So we'll use P hat. So we'll fill in our value here for P hat, 0.2175, 1 minus 0.2175, all over sample size, which is 800. And let's calculate that value. 1 minus 0.2175 all over 800, and we get 0.01459. Okay, so let's set up our confidence interval here. It's P, so P hat minus 1.96 times the standard error, and P hat plus 1.96 times the standard error. So let's fill in all of these values that we have. 0.2175 plus 1.96 times 0.01459 And the same on the other side, 0.2175 minus 1.96 times 0.01459. And my confidence interval here, let me just jump to the end, 0.2461 and 0.1889. Okay, so we're saying there between about 18% and 24% based on the fact that it was about 22% in the sample that we chosen. So that seems kind of reasonable to me there. Okay, so if we're taking away anything from what we've looked at here, the main things you need to know: confidence intervals for population proportion, so p hat minus error, p hat plus error, the fact that we can do that using our standard error, which is the square root of p1 minus p over n. If we need to or requested to, we will use the 1 over root n instead. Okay, knowing that in the log tables the standard error is given as so, however the margin of error, the 1.96 times that, is not given, so you need to remember to include the 1.96 within that. Okay, and beyond that, just a little level of understanding on what population proportion means and what it represents here.